Okay, here we have a quick introduction to vectors as it pertains to AP Calculus. A vector is very simply a magnitude but in a particular direction, often represented by an arrow. Wind or velocity or acceleration are often represented by vectors. We can break vectors down into horizontal bits and vertical bits and describe each separately as a parametric. So you will see that often position is given in this form. These little brackets are for vector notation. I think it's harder to think of a particular location or a path as a vector, but nevertheless, we introduce the position this way, often parametrically with x as a function of t and y as a function of t being time when we're talking about motion. So then the velocity is simply, as you'd expect, the derivative of the position functions, each with respect to t. Two different ways of saying the same thing, dx dt and dy dt. You can see more about this in the tutorial I did on parametric equations. Acceleration then is the second derivative. Again, brackets here indicate its vector notation. So the path of an object, curved path as it's described parametrically like this, you can think of some point on the path that the velocity is going to be described by a vector that's tangent to that path, if that's the way the particle's moving at that instant, and we can break that down, resolve it, and then express it with parametric equations. So the speed of the particle or its magnitude of the velocity vector is simply just Pythagoras, right? You can take and say, well, this is your x component, there's your y component. We square each of those, add them up and square root them, and that'll be the magnitude at some instant when t is equal to some fixed point a. So the length of a path that this particle is moving over time is then just going to be the arc length, the integration from a to b of, again, this is just the Pythagoras being applied here, where we take the derivative and we square that, and we take the derivative of the y component, we square that. But this is a function, this is not a fixed point. So integrate along that path, often done with a calculator. Very rarely does it work out that we can do it without a calculator. All right, so two examples here. First off, we have the position of a particle is given by these two parametric equations. Okay, be really focused on what we're given here. It's the position, so we can then find the velocity by simply taking the derivative of that. So my velocity vector is going to be what? That is going to be t plus 1. And the y component then, when I take the derivative of that, bring that 3 into the 1/3, it's going to be t squared minus 1. That's very convenient. The acceleration vector then will be the derivative of this. Second derivative of the position function, that's just going to be 1, and then 2t. Okay, so they get a little bit simpler. Find the magnitude of the velocity when t is equal to 3. So I just go up in here, plug in 3. That velocity at that instant in the x component is going to be 4. And then in the y component will be 9 minus 1 will be 8. So the magnitude then, when I hit it with the Pythagoras stick, is just going to be the square root of 4 squared plus 8 squared. So what is that? That is the square root of 16 plus 64, which is the square root of 80, which is then, when I simplify it down, take out a 16 and square root that 4, radical 5. So that would be that answer there. Find dy dx, but now as a function of x. It's simply done dy dx as a function of t. I'll start there. That's going to be dy dx will be then t squared minus 1 over t plus 1. This I can factor to be t minus 1 times t plus 1 when I break that down, and then the t plus 1's cancel, and I'll get t minus 1. However, I'm not done because I need it to be a function of x. So I have to go back up to my original and say, well, okay, if x is equal to 1/2 t squared plus t minus 4, the only way I can get this quadratic simplified down to a single t is if I complete the square. To do that, I need to divide by 1/2 or multiply everything by 2. 2x then is equal to x squared, or t squared plus 2t minus 8. Then to complete the square, I'm going to rewrite that as t squared plus 2t plus something to complete the square minus that same something minus 8. How do I complete the square? I take half of 2 and square that. So that's 1, and then minus 1. This I can factor down, t plus 1. It's not likely you'll have to do a completing the square type problem, but it is possible. Minus 9. Keep going then, so that's going to give me 2x plus 9 equals t plus 1 squared. So if I square root both sides, I'll get that. And then in this case, I can write the answer that t is going to be equal to the square root of 2x plus 9 minus 1. I did not say it up here, but it is really implied that t is going to be greater than or equal to 0. They will usually say that on an exam question. All right, so what do I do then? I am going to sub this back in up there, and so my final answer for part C is that y as a function of x, actually this is, well, yeah, this will be the velocity. I'll say dy dx as a function of x is going to be then the square root of 2x plus 9 minus 1 minus 1 more. So that would be it. All right. At what times is the particle on the y-axis? Okay, well, the particle will be on the y-axis when the x component is 0. So when is that going to be 0? That's going to be 0 when this quadratic is equal to 0. Again, I'm going to be solving a quadratic for 0. Right off the get-go, I'm going to double everything and say that's t squared plus 2t minus 8. And that is, thank you very much, going to be factorable. And that's going to be plus 4 and minus 2. And so my value will be when t equals 2, because t equals negative 4 is not in the domain. So that's when it will be at 2 seconds is when the particle will be on the y-axis. And what is the acceleration at this time? Go back up to the acceleration vector. And so acceleration at this instant will be 1, and 2 times 2 is 4. So there you go. Okay, that's example 1. And you haven't been able to see it. I'm so sorry. There it is. All right. I just took that quadratic and I factored it. I found that t was 2. I put it into my equation up here. Got the answer. All right, I'll be more careful on this one. So here we go. When t is equal to 0, a particle has a position. That's the location of its position, but a velocity. So this is not the same as the last one. And there's the velocity vector. And here t is also greater than or equal to 0. Find the parametric expressions for the position of the particle. All right, well, to go to the position, I've got to integrate. So this is sort of fundamental theorem of calculus here. If I integrate 1 over 1 plus t dt, what happens? Well, that is going to be what? The ln of 1 plus t and then plus c. And I know that when t is equal to 0, I'm at 1. So the ln of 1 plus 0 plus c equals 1. Well, the ln of 1 is 0. 0 plus c equals 1, so c equals 1. So the parametric expression, I guess I can kind of sneak this in here. My answer for A is going to start off being ln of 1 plus t plus 1. All right, what happens when I integrate then 1 over 1 plus t squared? Well, this is the inverse tangent, so that's going to be tan of t plus c. Well, I know similarly that at t equals 0, that is going to be equal to 2. Well, the tangent of 0 is 0, so now c equals 2 for this one. So I can write here that this one is going to be the inverse tangent of t plus 2. All right, so that's part A. Part B is eliminate the parameter and write as a position function as a function of y in terms of x. All right, so if this is equal to x, then I know that I can say x minus 1 is going to be equal to the ln of 1 plus t. How do I keep getting at the t? I'm going to raise e to each of those. So e to the x minus 1 is equal to 1 plus t. Take away 1 from both sides, and t then is equal to e to the x minus 1 minus 1. I then take this and put this in to my my function for y, and so then y is going to be equal to let's see, the ln the tangent to the minus 1 of e to the x minus 1 minus 1 and then plus 2. All right, so there I have the position for y in terms of x only. All right, again, trying to be honest, keep that on the camera.